happen, and then you're going to basically have the DNA incorporated into those. And then at the end, okay, these are two types of ways of getting the viral vector. There's ex vivo and in vivo. Just think ex vivo, outside in a cell culture first. In vivo, you're inserting it directly into the human. The ex vivo, they create the gene, they put it into a petri dish, and they take out a cell from the human. They incorporate the virus into their cell outside the body, and then incorporate the new one into their body when it's already been transcribed. Basically, they do the whole process that we talked about outside. And the in vivo one is the same thing we talked about before. They take the plasma vector, they inject it, and they hope that it gets taken up by the cell. It's inserted into the DNA. Okay, so we're going to go over transgenesis and cloning. Is the transfer of foreign DNA to totipotent and pluripotent cells. What I talked about is totipotents can be able to go into all return layers. Pluripotents can be able to differentiate into muscle, tissue, etc. Two types, fully transgenic and somatic cell nuclear transfer, which we'll go over after. And that's talk about Dolly, the sheep that was first cloned. And you need to make sure DNA is inserted into the germline cells. So basically that you can pass on DNA to your own. Okay, so this is two important factors of why transgenesis, why is it something that would be important. One is develop animal models of disease. So basically they're called knockout animals. So a knockout animal is you take a gene, say for cystic fibrosis. It's it's a one mutation in the body, and so you knocked it out of a mice who was previously healthy, and now you can have them have cystic fibrosis, and so now you can try to target, okay, how can we perhaps insert a vector or insert, to reverse the effects of cystic fibrosis. And then animal bioreactors, you mentioned this briefly, so it's called GTC therapeutics. Know about this concept, GTC, but so what it basically is you're trying to create proteins in sheep and cows or anything that produces milk, and try to get the protein in the milk, and so it's basically you're basically using the animal as harvesting the proteins that you want for genetic manipulation. Pronuclear microinjection. So there are two types. There's somatic cell nuclear transfer, and then there's pronuclear microinjection. You don't have to really worry about the pronuclear microinjection or somatic cell nuclear transfer. This is a less used model. If you want to get a fully cloned animal, you want to use somatic cell nuclear transfer. Okay, so how does it occur? So basically, it's really important to be a structural gene. You need a vector that we just spent 10 minutes talking about in order to insert the DNA. And you need a promoter and enhancer. And a promoter and enhancer is on DNA to upregulate transcription, upregulate protein synthesis, etc. And I'll go over these steps when we talk about Dolly. Actually, we'll do it. So Dolly, like I said, was created by somatic cell nuclear transfer, which is important if you want to get fully cloned animals. Okay, so here's Dolly. So basically, how Dolly was created through somatic cell nuclear transfer was they took a skin cell. So it's nuclear donor DNA from the skin. So it's important to remember. It's nuclear donor DNA from the skin of one sheet. Then they took another sheet and they took mitochondrial donor DNA from an enucleated egg. So they took an egg out of a female, removed the nucleus from the egg. So now you just have basically cytoplasm filled egg. But it still has mitochondrial DNA. They didn't remove the mitochondria. In general, you usually get mitochondrial DNA. Everyone in here from their mom because how genetics work. So what happens is they have the enucleated egg from the female. They have the skin cell, which is the DNA that's actually going to turn into. They inject it into the enucleated egg, and they do some kind of electrical stimulation to get the fertilization to occur. And then they take that, so that fertilization has occurred in each dish, and they get inserted back into the female, and it will grow up to be Dolly. Dolly was an offspring of the where they grabbed the skin cell. So it's not technically her DNA. And so these are the numbers. A little bit important. I'll look at them. So it really gives you an idea of how many trials they had to do before getting to one term. So they had 277 reconstructed embryos. So meaning when they took the enucleated egg and then at least only one birth. So it took all of that to get done. Okay, and this is just, we talked about this before, just kind of important to know about the reason why transgenesis is a popular topic is the idea that we could potentially have proteins that we're looking to adhere in the milk of sheep and cows. Any questions?
Cool, just looked like the first 2 or 3 slides.
Polymers is the ink for menisci, and do you remember what meniscuses are? Yes, I remember. They're right? So you can this is more remarkable. You can generate 3 menisci in 16 minutes, but the post-implantation healing is 4 to 6. So you can check out really fast, but in order to be fully effective and do exactly what you need to do, it takes about 4 to 6. It's not a static implant. It's not like some implant where you just put it in and leave it. This implant is meant to serve as a scaffold for healing. So it's not like you're just putting placing a cushion in your knee. Now you're making a scaffold and then letting your body do the replacement. So the scaffold itself, what is being 3D printed, is not just a polymer cushion or just a polymer shape hold in place for a scaffold. It also includes special proteins that will promote healing. And they're not just proteins, they'll be chemicals, chemicals, and those chemicals will draw in So damages to certain parts of the knee joint can trigger degeneration of other parts. So no one really understands the exact mechanism behind it, but if you know, if you hurt one part of your stress bearing part of your knee, for some reason that can cause another part to just degenerate. Questions? It's all in the Scientific American article. So, joints, why do we replace them instead of letting them heal? Well, a lot of the tissue, a lot of the components of these joints is crappy vasculature. And blood, as you remember, blood equals healing. Blood brings the growth factors, blood brings the materials to rebuild things. So without blood, you can't really go well. There's no real vasculature, very minor vasculature in the cartilage. And also the location is bad. So, like the ACL, for example, is located still located only in the knee joint, so as fluid pressure. And the problem with this fluid is it prevents clot formation, and clots often act as scaffolds, right? So if you have a clot, you want to release factors that bring in new cells and bring in new tissue, and it also acts as scaffolds that will use tissue itself to grow. But if you can't form the clot, you really have no chance of healing, and you can't form it. But if, you know, just to show that vasculature is really the main thing here, the outer region of the meniscus has some blood vessels. So if you get a very specific type of meniscal injury, there is a chance that you can just heal it up on your own without getting it replaced, without getting it pulled out. But it has to be the vasculature. So if you have inner region damage, which is avascular, you just have to go through the conference with your yellow and arthroscopy and the other things. Anyway. So the ACL will not heal if the joints come together. So that's just saying what these things will not heal on their own. You have to look through the form, you can break them out and put something in place. And you can this new ligament can be either from a dagger or from yourself. I think it's usually from the side of the hamstring or the patella. A little bit more on self-repair. So can we can identify why this cartilage, ligaments, tendons, we know why they can't heal. So can we override that? Can we make it so they can heal? What can we do? Use biologics. Biologics in this case are substances from the patient's own blood and organs. Right, so there's no immune problem here, it's just cell to cell. So platelet-enriched plasma, PRP, was first used to regenerate jaw components. What it really is, you extract platelets from blood, which is, you draw blood, you centrifuge it, you get the layers, you pull out the layer of platelets, which is the one you want, and you add some growth-promoting substances, and you apply that to the damaged area. Theoretically, that's supposed to make it improve the growth and healing. And then there's a different version, bone marrow aspirate concentration, the BMAC. What this forms is, if you draw it out from the bone marrow, it forms a thick clot. You add stem cells, you have growth factors, you use this clot, and it becomes like a paste, and you apply that to the damaged area. So PRP and BMAC are taken to the patient and re-given to the same patient, so there's no FDA regulation. Biologics promote healing, but do not yet fully repair torn menisci or ACLs. Make that through? All right, so the other article is on medical tourism. So, we have a story of a patient with severe osteoarthritis and he needs a hip replacement. So, he's searching for a relatively cheaper, not cheap, but a relatively cheaper hip replacement. And he finds that Oklahoma City is the go-to. Competitive fees, there's doctor and hospital, and through my PowerPoint. I'm gonna go through quick and just touch on the main points of the slide. I didn't make a separate review for PowerPoint, so sorry guys, you can stop taking pictures if you want. This is really just what's posted, but I'll be talking